And today we are going to be learning about BlockCoin, an improvement on the bank coin that we wrote last time. The two things we're going to focus on this time are writing a network protocol and distributing the authority that was so concentrated in bank coin, right? Remember, we just had one bank, which is how we eliminated double spends, but that in practice would never work because you don't want all the power to be in one set of hands. So in review, Bankcoin maintained all of ECDSA coin's biggest strengths, right? The issuance and transfer of coins was cryptographically verifiable, and that's really powerful, much better than PNG coin, where you had to inspect it visually, right, which is not good. It also improved ECDSA coin's biggest flaw, which was its proneness to double spend attacks. It was trivially easy to go and double spend your ECDSA coins, and therefore in a free market for money, they'd never accrue value, right? Who would ever use these things if you don't know if your coin is good or not, if there's no way to test it for yourself? And but it did have one big weakness, as I said in the intro. It introduced a monopoly. The bank will abuse its power, and so in this lesson we're going to try to move from one bank to many banks, and banks in quotes, right? These are sort of like the abstract idea of a bank. It's just like a centralized authority in our monetary scheme here. And the other thing is it still lacks an internet protocol, right? We were tossing around these coin files, right? It'd be like a file that could represent a coin, and you know, that's kind of hand wavy, and I guess you could email them, but we really want to fix that, and that's what we're going to start today. We're going to write an internet protocol. And so we'll be building directly atop TCP/IP, just like HTTP or Bitcoin does. They're both layers atop TCP/IP, and we'll get to that in a second. So what is this magical acronym? Well, IP stands for Internet Protocol. It's just a scheme to give every computer an address, right? So you can address the computer, so you can send information to a specific computer. And an example of this is this pair of numbers. Number. That's like the host name of a IP and an IP address, and 80 is the port, right? Because this would represent the machine, and this would represent like one program running on the machine, right? And so the idea is you'll want this pair to address any sort of program running on a machine somewhere, on a computer somewhere, so that you can direct your communications to any specific computer, and you can direct your communication to one of many different protocols that might be running on that computer. And so how do you do this communication? That's TCP, Transmission Control Protocol, and it's just a scheme for transferring raw bytes, where raw byte is just a number between 0 and 255, right? And then there are all kinds of schemes to give these numbers value, like they could have a value as in terms of a letter, like in ASCII or UTF-8. And so this is just a scheme to transfer raw data in the form of bytes between addresses using their IP address. And so in order to learn more about this, I'm not going to go into this very deep, but I would really recommend this Networking Zine by Julia Evans. And so if we open it, I already have it open over here. And so it's like this long, well, I'll just open it. It's like this long kind of cartoon of how this works. And I think it's really nice she does a great job explaining all these really complicated and dry concepts in an easily digestible manner. And so I'd recommend you just go through and read the zine or zine, who the hell knows how you say it, and you get a little idea of what's going on if you've never heard of this stuff. For example, sockets. We're going to be doing a lot with sockets. So I'd recommend you kind of go through and read this now. And in particular, there's this one slide with networking layers. And this is what I want you to really kind of understand and take away from this, is that you have all this, like this is what an IP packet looks like, right? At this top layer up here is like, it's actually not even in the diagram. This is like how this data is actually sent over wires like fiber optic cables or radio waves to your cell phone. And so this is really, really low level. And then at the next level, you have a protocol that your network card on your computer or your phone knows how to interpret, right? And you have these MAC addresses and stuff like that. And so you can see this is a certain amount of bytes, and there's a very precise format these transmissions follow. And one layer up is IP addresses, right? This is going to say, to which computer do I want, is to which computer and to which basically program running at some port do I want to send this, right? And so here's some stuff that we saw last time, right? Source IP address, destination IP address. These are that pair of numbers we saw earlier. And then you have something like a header checksum, right? This is just checking that this is a kind of a sanity check to make sure that none of the data contained here was manipulated in any way in transmission of this message. And this is something actually the Bitcoin protocol we'll learn in the next series where we do initial block download after this digital cash series. We'll learn how Bitcoin has similar schemes to this as additional sanity checks. And then there's something, how long is the packet? So when the listener is listening to all these bytes, when do they stop and say, okay, this message ends, the next message begins, right? And so this is really complicated stuff. And here's the next layer is TCP. This is what we're going to be using. And here you go. This is the ports and the length, and there's just a little more stuff here. And then below is the raw bytes in the message. And so this is like completely unstructured. And if you see here as an example HTTP, this is where they say, hey, this is a GET request. GET is a GET request. That's when you load up a web page. Or for an example, you might have a POST request. Right? That's when you submit a payment form. You'd be submitting a POST request. These are all of the. This is where the higher level protocols like HTTP or Bitcoin have free space to do whatever they want. And so this is where our protocol will be operating in this kind of free space of raw bytes transmitted over a socket. And so if some of that doesn't make sense, that's okay. Just understand what you can and try to follow along, and hopefully some of these hands-on examples will help you understand these really deep and also dry, oftentimes kind of boring ideas in network programming. Like the first time I encountered most of this stuff, I just wanted to fall asleep. So hopefully I can make it a little more fun. So jumping back into the slides here. So yeah, read that, and in this class Slack group and in our little Google Doc for the class, I'll try to post some more stuff. And so here we go. Last time we made Bankcoin. This time let's make BankNetCoin, right? Like a really corporate. I purposely make some of these names really corporate-y sounding to make you, libertarian Bitcoin freaks vomit a little bit. But here's BankNetCoin. BankNetCoin. You don't see the .com at the end there. BankNetCoin.com. So it's a protocol built atop TCP/IP. It lives at layer 7 of the protocol, right? If we go over here, remember, the lowest level was wires and radio waves. Highest level is email, HTTP, stuff like that. Bitcoin lives here too. And so it lives at layer 7, just like HTTP and Bitcoin. Every message in our protocol will have 2 attributes, right? It'll have command and data, right? Like this basically just means like what message am I sending and what data is included in that message. And this is really similar to how the Bitcoin peer-to-peer protocol works as well. Every message has a command, and every message has data associated with that command specifying exactly what the sending client wants done. And so a difference with our protocol, with Bitcoin, there's a very raw custom serialization format and schema for every message that we'll learn a lot more in that next initial block download series, where we're going to implement initial block download in Python, at least a subset. Our protocol is not going to do that because it's just a lot of work to make such a custom thing. We're just going to use Pickle, Python's built-in serialization library. And just if you're not familiar with the word serialization, it just means take something that's like an object in your programming language and turn it into a raw binary aka bytes, a binary format that any computer that you can send over TCP/IP, right? Like that's the idea, is you transfer raw bytes. And so that's what Pickle does, is it takes a Python object, and basically any object, which is what's really nice about it. It's very, very little work to include in our protocol. And so it'll take a Python object and turn it into bytes. And then we can send that over a raw socket using TCP/IP. And so we do this for a convenience because our toy project is not about network programming. We do a little bit of network programming, but that's not the focus. What we really want is to paint this big picture, and we'll fill in more of the kind of the details later. But that's the hardest thing about Bitcoin, right? Is that there are so many different aspects to it that, you know, you kind of have to do the broad strokes and the big picture first, and that's what we're doing here. And so this decision is acceptable for our toy project, but never in real life. You'd want something much more general purpose, right? Like if someone's trying to write a client for our banknet coin in JavaScript, they wouldn't be able to, because JavaScript doesn't have this pickle library. So, you know, if some of you guys are looking for an exercise, a good exercise would be to remove pickle and replace it with JSON serialization or something like that. And then in your, you know, I know a couple students, one student's working on a Rust implementation, another one's working on a JSON or a JavaScript implementation of this stuff. Then you could actually have these different libraries interoperate on the same network, which would be really cool. You know, you have different clients in different languages, but the network is standard, and so everyone could participate. And so here we go, right? Magic internet money, right? Banknet coin, come join us. So that's what we're gonna get into here. Okay, so let's jump over to our terminal and get started. And before we write any new code, I want to tie up a couple of loose ends from last time. One of them was a bug that was in the code, and another one was a modification I made to the dependencies so that we don't have to do that public key.toString hack all the time. I just made a fork of that library and added a convenience function that will allow us to compare public keys directly. And so I'm going to demonstrate both of those to you right now. And so in order to do that, I want to open up a new test case that I wrote. And so it's called banknet coin tests. And I already have it open, so Vim gives me this message. And by the way, you can use any text editor you want. You don't have to use Vim. And so here's the new test case. And so currently it's importing from Bank UTXO coin, the thing we ended up with last time. And so there are two test cases here. And the first one, basically, just like last time, we go and create a transfer where Alice sends 10 coins to Bob, right? And that was a perfectly good transfer. But we're going to do one other thing. We're going to say, like, let's say somehow Bob manages to get a hold of this transaction. Like maybe he's snooping on Alice's email or something. And before she can send this email to the bank, tell the bank about this transaction, he goes and he modifies the amounts in the outputs, right? And so previously, the first output was 0 was 10 to Bob. And so he's going to go and say, hey, for that output, I'm going to say that's 990. I'm going to say that instead of leaving Alice with 990 change, I'm going to give that all to me. And where the second output was the 990 change to Alice's key, Bob's going to say, well, Alice, you keep 10, right? So he goes and like modifies this transaction afterwards. And what our coin should do is it should, if you do this, now all of a sudden the digital signature should no longer verify, right? Like these amounts should be kind of like locked into the digital signature that Alice signs the transaction with. So if the transaction's tampered with in any way like this, then you'll get this, right? When you try to run bank.handle transaction, it'll raise a bad signature error. That's what we want to happen. And so if I go run over here to a different terminal, and so first we want to turn on our virtual environment if you're using one of those. And then we want to do pytest banknetcoin.py. And so when we run this, we're going to get two errors. These are test cases that should pass, but neither one of them do. And that's the problem here is we get to this bank.handle transaction, and it actually doesn't raise a bad signature error. It says, oh, I'll just believe whatever these amounts are, right? Like you can go and tamper with the amounts all you like. And so there you go. There's a big bug that I left in my code last time, and we're going to fix that now. And so we'll ignore the second failure right for the moment. And let's go back to our terminal, and let's go and make a copy of this Bank UTXO coin. We'll leave the old one pristine and untouched, and let's go make a copy of this and open that. So what we want is CP Bank UTXO coin. Let's call it MyBank. So we're going to copy Bank UTXO coin, and we're going to call it MyBanknet coin. And so this is what we're going to be working on for the first half of this lesson. And so let's copy that, and then let's use Vim to edit that. Or let's use whatever the text editor of your choice to edit that. So my banknetcoin.py, and I'm going to split the screen here and also open up the banknetcoin tests, the test case we just saw, right? That where we have this test case we need to fix. And so I'll kind of get into why. So that's the question, is like, why is this allowed? Why can you tamper with amounts afterwards and the bank will still believe that this was Alice's true intention, right? To give Bob 990 when she only meant to give him 10. And so the reason that happens is if we go over here and look at the sign input method, right? This is where Alice would be signing her digital signature, giving her intent that she authorizes this transaction, right? And the message she sends is the TXIN, right? That grabs the TXIN, and then the spend message according to that, associated with that TXIN. So when we go down here and look at the code for spend message, it's just like, it just creates a string containing the information, basically a pointer to which output she's spending, right? What's the TX ID of the output she's spending, and what's the index? And so the problem here is that there's nothing about the TX out, the out that she's authorizing, right? Like, there's nothing in the message she's signing that declares where she wants the money to go, right? And that's why you can tamper with the TX out, right? So if we look to line 32 here, Bob can go and tamper with the TX out, and our digital signature scheme doesn't forbid that. And so that's a huge bug. And, you know, first version of the class, there are going to be some bugs like this. And so, but I think it's instructive to go and fix this. And so what we really need to do is we need to change the message she's signing. And so in order to do that, what we want to do is we want to create a message that's more like, you know, that, you know, is kind of like, it's like message equals we want it to include the TX in that she's signing, but we also want it to include all the TX outs that this transaction specifies, right? And so that way, when she signs this data, right? And this is hand wavy. We need to actually serialize this and turn this into bytes that the ECDSA library can sign, but the inputs have to be something like this in order to really lock in what her intent was. And so that's what we're going to do. So we're going to create a new spend message, right? And we have to create it kind of outside of the context of this TXIN class because it has to know about the TX outs, right? Where the money is going. And within TXIN, right, that stuff's not available. And so what we're going to want to do here is we're going to want to let's create a new method called spend message. And so as an input, it takes the transaction and the index, which the user will want to sign with their key. And so the first thing we want to do is we want to grab that out point. And I'll just, in order to see what we're doing, we're just going to copy this. This is how you grab the TX in. And so let's just do that. So we'll grab the TX in, right? And instead of self, we need TX. And so now we're using the arguments of this function. And now we want to grab the out point, right? Like this just basically says which UTXO are we spending. And remember, out point is just this property. It's like a function that you can call, but since you decorate it with property, it means you don't have to put the parentheses afterwards. It's just like a little syntactic sugar to make stuff a little easier to read. And then so the other thing we want is we want the TX outs, but we already basically have this, right? Like it's just, right? So we don't really need to write that. And so what we want to do is we want to kind of mash these together and turn them into bytes using some repeatable scheme. And that's going to be our serialize function that we wrote last time, right? Remember in the library we said we're using pickle. That's what if we just go and just open utils. Remember, serialize just says pickle.dumps, right? Which just says, hey, I'm going to take a Python object and turn it into bytes. That's all this does. It's just a little review. And so what we're going to return here is we're going to just serialize the out point and the tx outs, and that'll give us raw bytes, right? It'll look like this, you know, with a b out front. That's a byte string. And so the good thing about byte strings is you can add them, right? Just like a regular string. And that's legal, so we can just add them. It doesn't, with this message, it doesn't matter exactly what the final product looks like. It matters what the inputs to that were and whether it's reproducible. And so the inputs will be the out point that we're spending and the tx outs that we're creating with this transaction, and it'll be reproducible because we're using serialize, and that's the native super reliable Python serialization library. And so that's kind of what our spend message is going to look like, and we're going to want that to replace this. So let's just go ahead and delete this spend message since we're replacing it, and then we'll go and replace every instance of this with our new thing. So let's search for spend message. And we'll start at the top. So here's our new function. Okay, so this is our first instance in the sign input method. So what we're going to want to do is let's remove that and just replace it with a message variable we'll define. And so message is going to be right. We're going to pass in self because this is a method on the transaction class, right? And spend message takes a transaction as the input, and so and then the index, right? Because that's the other thing it takes. And then so that's our message. That's what we'll sign, and then this just tacks it on to the transaction's tx ins. And so there goes. We've replaced our first instance of the thing, and you know, now we can no longer fiddle with these, right? Because they're locked in as a commitment to this message we're signing, just as, again, to drive this home. Now, once we do this, Bob will no longer be able to fiddle with these because they're the old values, these values, are going to be locked in to the message that Alice signed. And so let's look for our next message or instance of this class, or this method. Let's go and create a... Well, so let's stop here. So this is the problem thing right here, right? So let's kind of do something new here. Let's go and, instead of calling public key.verify here, let's go and just put this responsibility onto the transaction class, right? Because we already have this tx.sign input, right? So like, here is tx.sign input, right? So let's just write a new function that can do verify input, just so our API looks pretty consistent and similar. See how this looks pretty good. And, sign input, right, was index and private key. Verify input will be index and public key. And so that looks pretty pretty consistent. And so the code will look quite a bit similar. So the first thing we'll do is the first thing we need to do is grab the tx in that we're signing. So and then the next thing we need to do is produce the message, right? We can just copy that from up here. Right? We can just pass in self and index just like we did above. And so you can see here, it's really nice. We have, when we're creating messages for signatures, and then when we're verifying messages, we produce the message in the same way. Just to, you know, that's the key here. The message is always going to be produced exactly the same way. And then so what we're going to do is we're going to just return public key.verify since we have public key as an argument here. Okay, so there we go. We have tx in already, so we're going to just grab the signature that we're verifying, and then we're going to pass in the message that we just calculated, and we're going to check whether they match. And so So let's run over to our terminal again, and let's try, I think I did everything. Let's try to run this. Okay, I know what happened. And so what the last thing we want to do here is we want to, you see previously we were importing from bank UTXO coin. So we want to just switch these two imports. We want to now start importing from my banknet coin, right? This file, see down here, bottom left in Vim is where the file name is. This is where we want to import these classes from. And so hopefully now, you know, basically the same code, but with one modification, hopefully we'll be able to get this first unit test to pass. Got one little bug here. And so, sorry, yeah, index here is not defined. And so what we're going to need to do is this is a little ugly, but so enumerate will go and iterate over this, and instead of just returning the elements, it'll also give you an index. And that way we'll be able to pass that in as an argument. And so there we go. Where we previously had 2 failures, now we just have 1 failure here, right? So I'll just clear everything. And see, now there's only 1 test failure, right? 1 failed and 1 passed. And so now what that means is when we did this pytest.raises signature, bad signature error, that means when we told the bank about this, it raised an exception. It says, hey, sorry, the signature's bad. I'm not going to accept this transaction. And the balances won't change. So that's really good. The whole thing will blow up, and that's what we wanted. So we fixed this 1 bug, and that's a really important bug, right? It allows us, it makes the coin much more secure. And so the second thing we want to do is we want to look at this next test. So let's just run down here a little bit. And so what we do here is we take Bob's public key, and what we do is we turn it into a string, right? Remember, we do the 2-string hack. And then what we do is we call verifying key.fromString and just specify what parameters to use. That's what this curve is. And we get a derived public key, which should be it's like exactly the same, but it's like a copy of the thing. It's a copy of the public key. And so, ideally what we want is we want to just be able to say, you know, public key equals derived public key, right? But what we saw last time is we needed to cast them both to strings in order to do comparisons, right? And so this is what's failing. This is true, obviously, right? Because last time it was always true. But this is not true because they're 2 different objects. And so that's what you see here, right? The second assertion, this assertion works. The second assertion fails, right? And so I have a pretty easy solution here. So let's clear the output and look at the requirements.txt. So this is what we used to be using for our ECDSA library, and this is what we want to use. This is just a little fork I made, and I made 1 commit. And the 1 commit I made just adds this dunder EQ, and it just checks if the 2 strings are equal. And so that's a little thing we went over last time. And so this is great. Now we don't have to do this every time we see a public key. We just have to do this once in the fork of the ECDSA library we're using, and now we can compare public keys directly. And so this is how you can include like a GitHub URL in your requirements.txt. And so now if we reinstall the requirements, we should get this new updated version where we have this cool new thing. So what we can do is we can just uninstall the 1 requirement that we don't want anymore. And then we can install all the requirements. And you'll see the one thing it did is it said, I need to go and get ECDSA. And so it went and installed that. And so now we have the new fork version of that library that should help our unit test pass. So remember, this is what we're testing. So let's go over, clear the terminal, and we should just be able to do pytest, right? And so there we go. Once we installed the new fork that has that little 2 lines of code, now our test passed, right? The public key and the derived public key are equal when you compare them. And so that's going to improve our code. Now we can delete all those instances of 2 string. So like over here, remember we had 2 string over here. We can just delete those 2 strings and it'll work. So that's really good. Those are two loose ends from last time. Okay, so now let's get to business. Let's figure out how to write an internet protocol that can expose the bank to basically any user of this coin. And this is this is the really getting to be the one of the core aspects of Bitcoin, right? Bitcoin is a peer-to-peer network that runs directly atop TCP/IP, and that you can interact with by writing a little bit of code using sockets in your Python program. And so we're going to be, this next section is laying that foundation in the context of our silly little bank coin here. And so in detail, what we want on our bank class is we want to be able to expose these methods: handle transaction, fetch UTXO, fetch balance. We want to be able to expose these over the internet so that somebody can go to our bank and say, hey, I have a transaction report. Could you execute this for me and update the balances, right? And after that's done, they could say, hey, I gave you a transaction. What's my new balance, right? How much money do I have? And so in order to do that, we're going to write a simple little socket server outside of the code base here, just as an experiment. And then we'll take the code that we write and we'll basically we'll integrate it back into this program. But in general, with programming, it's oftentimes more helpful to write a prototype outside of the big complicated project you're working on, and that's what we'll do here. So if you just quit everything and you ls, you'll see this folder called experiments. So let's just cd into experiments. And if you ls, you'll see a couple files here that represent the different steps we'll take. And by the way, whenever we're writing some code, we'll be writing something like my ping pong. That's the next thing we're going to do. If you look at, there will always be a file without the my in front that will have the kind of the solutions. So if you're stuck, you can always go find what the correct answers are. And so this is what we're going to, let's just open it here real quick. And so this is what it's going to look like. It's just a little socket server. It has a server here that can handle certain types of messages. If it gets a ping, it'll respond pong. Right? It's like the simplest type of server, right? And if it gets any other type of message, it just ignores it. And so then we'll write a client that can actually send that ping message. And this is all directly over the TCP/IP network. These are some secret parameter or some kind of magic parameters that specify that. And here is the address that we talked about earlier in the intro, right? It's a host name, right? This is like an IP address, and this is just like the your local machine, and this is a port number that we're going to be running the program on our machine. And so let's quit this program and make a my ping pong and implement this. So if we just do my, we'll have a fresh new file and we'll implement this. So the first thing what we're going to want to do is we're going to want to let's go to the top. Let's import socket. Let's import socket server. So this is like a thing that can make a server that listens on a socket, like a port number on your computer, and can respond to TCP messages in our case. And so this is how you write one. And so all this does is whenever it gets some data, it'll call this handle method, and handle will do whatever you want it to do. And so here we're just going to say, hey, got a message. And let's just say, say what message we got. And so we'll just listen. We'll just receive 10 bytes. This is how many bytes you want. And since all we're talking about is ping and pong, each character represents a byte. And so we only need 4 bytes for our scheme. And so so that's all we need. And now let's write let's write some code that can actually run this server. And so the first thing we do is we instantiate this TCP. We instantiate a server using this handler. And here's address. We need to define that, but I'm just going to stick that in. And this just runs the server. And so for address, remember we had that earlier. So host is going to be, let's just run it on port 10,000. You can run it from ports like 0 to like 65,000. Like above like 2,000 or so, or below like 2,000 or something, they're like reserve ports, so you can't run on that. 10,000 is like right in the middle of the range, and hopefully won't collide with anything that's currently running on your computer. And then, so address is just a tuple with both of those. I think it can also be a list, but we'll just use tuple. So there we go. We have address defined, and so now we just need a way to call a server when someone runs the file. And so in Python, you have this little thing. When you run a file, there's this dunder name attribute that's available in the global namespace, and if it's equal to main, that means that this file was executed like on the command line, and so that means the user's not importing it from somewhere else. And we'll just run serve. And so if that works, this is not a ping pong server yet. This is just like a log and output whenever somebody sends a message. And so let's hop over to the server here, and let's go to the experiments folder. And there you go, my ping pong. And so if we call that, so look, it's sort of like doing something here. We didn't get any output, it's just sitting there. And so if you open another terminal window, you can say telnet localhost. This just means like my computer. And then what port, and it'll sort of open up a connection. And so you can see trying localhost. This is we're just going to like ignore some of these details for the purposes of this course. It's just your own computer, and now we can send over messages to our server. So like, hi, right? Oh, look at that, hi, with some stuff on the end. And so if we go over here, and if we want to remove this stuff on the end, which we probably do, we could say .strip. That'll just remove all the white space, right? Like this is a new line character. I forget what this /r means, but it's similar. And so if we kill this script and run it again, we should remove the white space after calling the strip method. But no, look at this. We get an address already in use error. When you're programming with sockets, sometimes your operating system will kind of reserve the socket that you just were using for a while. And so if you try to run the script, if you try to kill a script and run it again really quickly, you'll run into this error. And so if we run over the documentation for this, is for if you just Google socket Python 3 socket server, this is just the docs we're using, or the docs to the library we're using. And so if we go here to this, look at this allow reuse address on the base server, and so TCP server inherits from base server. You'll see this allow address reuse, and this is whether the server will allow the reuse of an address. This defaults to false and can be set in subclasses to change the policy. All right, so if we want to get rid of if we want to be able to reuse addresses quickly, we need to set this, we need to subclass our TCP server, the TCP server class, and just flip this one variable to true. And so let's do that. So instead of, so this is the class we're talking about, TCP server. And so let's just do it right here. What was it? Allow reuse address. I'll pause a little so you can type that out. And just set that equal to true. And then so down here, we're just going to use that. See, instead of socket server.tcp server, oh, I'm sorry, one other thing we have to, this has to inherit from the thing we're subclassing. Oops, socket server.tcp server. So this, we're just making a child class. It's the same in every way, but just flips this one parameter, which was what the documentation said, right? And can be set in subclasses to change the policy, right? Defaults to false. And so we're going to set it true so we can kind of like kill and rerun our script a bunch. And so now that we have that, let's and now if we run back over here, we should be able to run it, telnet in, say hi, right? Now we get no white space at the end, which is good. So now we'll be able to compare messages and check if they're ping. And if we kill this and run it again, now we don't get that error again. So it's another little hack. I mean, and you know, this is a very hands-on class, so I'm not going to do this stuff for you and like, you know, have you import the solution. We're actually going to do it each time. And you're going to do a lot of stuff like this if you're doing any sort of network programming with Bitcoin. Like, you got to get your hands really dirty in order to get the job done. And so now we're here. We have a handler that can respond to messages. So let's send pong if we receive ping. If we get ping, and that's how you can. This is a way to send a response, and we're just going to send pong. And so that's pretty simple. This is a ping pong server. We can kill it. Well, let's just start from scratch here. And then we'll telnet again over here. And then we'll say hi. And then, look, close. We didn't get anything. Telnet again. Ping. Send ping. Oh, it says got ping. And then look here, we got pong. Right? And the reason why it's kind of cut off here is that there was no new line character at the end of pong. And so let's just correct that. \n is a new line character. And so now that we have our socket reuse set up, we can just quickly rerun our script. Look, we're already saving time. And telnet in again, say ping. And now look, we get pong with a nice new line character. And we have a ping pong server. This is like really... this is the foundational level raw network programming that you're going to need to learn to do to become to do some real serious Bitcoin network peer-to-peer network programming. So these skills are not just some useless crap I'm teaching you for our BlockCoin and BankCoin experiments. There's a reason I'm teaching you this stuff. So the next thing we want to do is we want our socket server to we want to know how to access our socket server from Python, not use the telnet utility, which has been very helpful so far. But we want our program to be able, in the end, we want to be able to create many different socket servers and actually have a peer-to-peer network running on our own computers, because in the end we're gonna need that to implement our little mini Bitcoin. And so the first step is, how do you connect to a server? Like, we can run a socket server using Python. It's just this little bit of code. How do you connect to one, right? How do you send a message, just like we were doing with telnet? And so in order to do that, let's create a new function. Let's call it ping. So what we're going to do here is create a socket, an instance of a socket. And so the first thing we need to do is import socket. I think I already did this when I was debugging something previously that will get cut out. But so you want to import socket at the top of your program. And so the first thing, we'll create an instance of socket. So an instance of socket.socket. This is like the raw, think of it as like the raw tunnel across the internet that you can access from your Python program. Not a very scientific definition, but it'll do. And so it takes two parameters. It takes basically what kind of addresses are we talking about? Like, what version of what addressing scheme are we using is the first parameter, and the second parameter is what protocol we're using. And so if we hop over to the documentation here, So here are some of the examples of that first parameter. These are the two most popular ones, AF INET, and so this is internet. This is just the IP protocol, right? And this is the normal IP addresses, and this is an IPv6 address. They have colons in them. They're much longer. They were invented about a decade ago in order to prevent. We were going to run out of IP addresses, so this scheme has many more possibilities, and so this is a different scheme. And Unix has its own little addressing system, which no one really uses. And so for that second parameter, here are some of the options. The two most popular are sock stream. This is TCP. Sock dgram is UDP. The difference between UDP and TCP is basically the main difference is TCP guarantees that no packets are lost and will retransmit if anything wasn't transmitted. UDP doesn't have that guarantee. So, for video games, sometimes UDP is nice, but generally most people use TCP. And then sock raw is just like, you just do your own protocol, So for something like maybe like WhatsApp or Telegram, they have their own very low latency communication protocols. They probably are operating with something like this. And so we're going to want AF INET for our first parameter and sock stream for our second parameter. So let's fill those in. Okay, so we have our socket, and so now what we want to do is we want to connect to our server. And so on line 6 above, right here, we already have that address, so we just want to connect to that. Pretty easy. And now let's just send. So that should send ping. And let's then just receive 10 bytes like we were doing earlier, and let's print what we get. I think I got that right. And then instead of using telnet, let's use well, here's our problem, right? So so right now we have this ping function defined, but like now how do we call it, right? By default, when we run the script, we were just doing serve every time. So what we're going to need to do is we're going to need to parse the command line arguments. And so let's just say, if we're typing it, so let's say serve, let's do it like this. So if we type it like this, it'll run the server. If we type it like this, it'll run ping. And so the way to do that in Python is you have this, there's a library called sys, S-Y-S for system, that has an object in it that basically parses these out. So this would be the 0th argument. This would be the first argument. And so how to do that is we import sys, and we go to the bottom and say command equals, right? Because we want the first argument. That would be this one, not the 0th argument. Python's not included because that's kind of assumed. And so, so we grab it and say if and so that's what we need to do to be able to run it. So let's try that again. Oop, socket. So up here we needed, this was socket.connect. I was calling the modules socket. So we actually need the instance here, sock. Sorry about that. So look at that. If we run it with ping, all of a sudden the server will say, got a message, ping. And since it was ping, it says it sent a pong back. So now we have a Python program that can both run a socket server and can talk to the socket server. And just to demonstrate the change we made, if we run this here, it'll blow up basically. And so what we need serve. And so that'll run the server and just do it all over again. Receive pong. So there we go. We have a ping pong server. This seems like really basic, but this is going to be the foundation of a ton of network programming we do in this class. And so, if any of that didn't make sense, go read some documentation, and I'll post some tutorials if you want more practice. But in general, it's like with this stuff, it's like you want to solve a problem and you figure out how to do it. And a lot of this stuff, like I don't really remember exactly how to do it afterwards. It's like you figure out how to do it and then you kind of forget. And so, I don't expect you to remember all this. Okay, so let's jump back to our text editor here and open two files at the same time. So on the right, we're going to have my ping pong, the thing we just made, and on the left we want my banknet coin, right? The file that we started editing, we made this spend message, and this is going to be this is where we're going to implement a really basic internet protocol for our stupid bank coin. And so basically, in order to do this, we pretty much just have to copy and paste. So like first things first, let's do the imports. So if we copy those, we can put them all on the first line. These are all standard library, and we're just importing the whole module at a time, so those can go together. And then the rest of this stuff, right, we can just basically copy all of that and go to the bottom of the file, right? The way it worked is like we just have basically all that we have here is tx, txin, txout, and bank classes. That's all we had last time for bank coin. Bank UTXO coin for the last thing we made. And so if we just make a couple lines here at the end, we can paste in everything that we had, and we can basically put our networking code at the bottom of the file here. And so there we go. So we now have a ping pong server within our banknet coin file that should work. And we haven't modified it to do anything bank related, but let's save the file and let's go over here. We got to go back to the parent directory, and let's say Python banknet. We need my banknet coin, and then we want serve, right? And so it looks like that's serving, and then and then ping. Okay, good. Received ping, receive pong, ping, receive pong. So that's working. And so now what we want to do is we want to make this do something bank related. And so what we can do here is we can make a new section here and say, let's say, actually before that, instead of every time, actually let's do it this way, yeah. So now we'll go and do this. So the one thing that's kind of tricky about where we're at now is that when a client sends our server some information, we're basically just treating it as a blob of binary text. And so just a blob of text, really. And so the problem is like, what if they include some parameters, right? Like this is really the case we want. Right? This is the case that we want to handle, and this is where we're going to need, like, where are we going to get the transaction data here? It's kind of tricky. What we really want to do is we want to send, basically, let's send a dictionary. Let's send a Python dictionary with every one of these messages, and let's serialize it when we send it and deserialize it when we receive it. And so if that doesn't make sense, that's fine. Just follow along. So let's make a function def. And so that's the dictionary I'm talking about. It'll have two keys, command and data, like, if we go back to the intro presentation, right? When we said here, every message has two attributes, command and data. So now we're actually implementing that. Our simple protocol will just have every message will have two attributes. And so let's do it here. So when we actually send a message, let's make a, and so this is what we do this time is our command would just be ping, and our data would be empty because ping doesn't really have any payload with it associated, like a transaction would, right? Or even like a fetch UTXO or fetch balance command, right? These would have a public key associated with them. And so there's a lot of cases where we want to be able to pass two different commands, like two different parameters, like what the command is and then what's the argument to that command. And so now we have a message. Now we send the message. And we're gonna want to actually serialize it as well. So actually, let's do. Right. So this turns the dictionary into bytes that we can send over the wire. And we'll send that, and so and then here we'll say, instead of saying decode, let's say let's deserialize it, right? And these were just functions defined in our utils packages, or our utils file that we've been using quite a lot. And so this covers the case when we're sending pings. But now what about when we're receiving them? So here, this will be, let's call this like raw message. Let's call it message data, and then we can do this the same down here. Just so we're consistent everywhere. So we get the message data, we deserialize it, and that's the pretty dictionary that we're going to print out. And so up here we get the message data, we deserialize it, and then we say, hey, here's the, that's what we got. And then we'll say, instead of comparing with a raw string or a raw, instead of comparing the whole message, we'll say if message of, if the message is, if the command key in the dictionary is equal to ping without the B, because this is just going to be a string now, then we'll send back okay, so if the command is ping, we'll prepare a message, right? Which just creates a dictionary with these two keys. The command is pong, and because pong doesn't really have any data associated with it, we'll just leave that as an empty string. And then the serialized, so then we'll serialize it, that dictionary, and then we'll send that directly over the wire. And we'll delete this because that will be a syntax error. Okay, so let's see what happens when we run this. So first let's run the server, Python banknetcoin, mybanknetcoin.py serve. Okay, so no bugs so far. Let's pray and hope that that continues. And so Python mybanknetcoin.py ping, and so that'll ping the server if I didn't forget anything. And I did forget something, deserialized not defined. And so that's up here. Got to import that from utils.py and save the file. Let's go over, try again. I'm sure there will be something else wrong, and there is. And so yeah, so we're running the pickle is not receiving enough data. Like our deserialization method is not receiving enough data, and I can bet what that problem is. So yeah, remember in our first version we were just getting 10 bytes at a time, right? 10 bytes was sufficient when our message was just like the byte string ping, because each letter is 1 byte, and so that'd be 4 bytes max, and so that's enough. Now we're getting a dictionary back, a pickle dictionary. Let me just demonstrate this to you for you guys who don't really know what pickle. So import, or let's, yeah, so we'll just do import. So that's basically what we're dealing with there, that D object for dictionary. And so then pickle.dumps, well, this is what it'll output, right? You can kind of see command in there, ping. You can see a little bit what's left, but this is just like, these are just raw. Each one of these /x's is a byte, right? Like you can see that the numbers are all, well, actually maybe not. Yeah, I mean I'm not sure exactly, but I mean most of, like, this is just a 0 byte, right? And so there's a little bit of other stuff going on. I'm not quite sure exactly what each one of those characters means, but you can get a sense, right? You can get the length of it. And so 51, right? And so this is 51 is greater than 10, so that's our bug. And so what we need to do over here is, instead of getting 10 characters at a time, let's get, I don't know, 5,000. That, hopefully that is, I think that's within the limit. There's a number, I think it's like 6,000 or something, that maximum characters per TCP message. Hopefully that's not in above the limit. So we can kill the server, run it again, and I think I saved the file. Hope I saved the file. And then ping. I did save the file. And so there we go. It worked. So we have a, got the message, command ping, data nothing on the server side. On the ping side, you get a pong response. Command pong, data is nothing. And so there we go. Now we're starting to get a little bit more of a protocol, because we've not only do we have a transport method defined, which is TCP messages, we also are starting to define what the format of those messages are, right? We pickle a Python dictionary with 2 keys, command and data. And so now let's do something that is actually for real. What if we said, instead of command, what if we said like balance, like get balance, right? That would start to be exciting. And so let's kind of do that right now. Okay, so first things first, let's update the handler to be able to handle a balance message. So we'll say if message, let's just go like this. There we go. So if command is equal to, if we get a balance message, let's say, we can say, over here, it's probably better to call this response too. Oops. Let's just refactor that really quick. Yeah, that's a little better. We'll call it response instead. And so I think what we want to maybe do here is, let's sort of let's make a, yeah, instead of like one option would be to copy and paste all this and do it all over again. That gets to be kind of a pain. So let's write a respond method on our actual kind of handler class. So and then so we can basically say, we can take all this, paste it up here, and right, and prepare message, we're just going to pass in whatever we got as the arguments, right? And then so we will serialize it, and then we will send it, right? And this doesn't really return anything, so we don't have to return it. We'll just call that. And then so here we'll just say self.respond, right? So look at that. That's kind of all of a sudden a pretty nice kind of a visual improvement there. And so here we'll say we'll have to grab the public key, right? We'll say for this type of message, the data associated is just a public key. And so obviously we haven't written any logic here, but that's what we're going to define as what's happening. And then so what we want is we want to call bank dot balance equals that, and then let's respond self dot, let's call it balance response. That'll be the command name. And then let's actually give the balance as our data. And so this would actually implement the responding to these types of messages. There's a couple of fuzzy things right now. I mean, the biggest one right here is there actually is, we don't have an instance of bank, right? And so this is a little tricky. And so this is a hack that we're going to do. But what we're going to do is we're just going to say bank equals bank, right? We're just going to create an instance of bank in the global namespace and then have it addressable by anybody. And so this is a little bit of a hacky thing to do, but it's simple, and that's what we're striving for. Simple and clear. So, we're not engineering a real system here where you wouldn't want these global variables floating around. So that works for now. And so that solves that. But the other thing now is actually at this point, bank is not going to have any. It's just going to be zero. There's no transactions in the history yet. So in order to facilitate our experiment here, we're going to want to alter the. We're going to want to make some fake transactions when we spin up the server. And so what we're going to do here is we're going to say from. Actually, we can just implement this at the top. So I'll just show you this file. I made a file called identities.py with just some little helpers to kind of help us with our simulation. Here's a function that will take a name and return a private key associated with them. Sometimes we want to get Alice's or Bob's private key. Here's another one that can get a public key. This is this one will come later. Those are for the next version of the video, or the next section. But so what we want is when we run the server, we want, did I import that from? So we'll import this user public key, right? And so what we want is we want to get Alice's public key when we run this. So we'll just say for Alice. It's kind of a hacky thing, but it's you can think of this as this would be a database you could look up different people's public keys in. Not that crazy. And so what we need, so this is the really hack is we're going to issue Alice 1,000 coins. Right? Because we need some balance in our system here in order to play with it at all. So, we'll just say hack, that's what you do. So that should be good. So now we have, Alice will have some coins, so we can actually fetch her balance. We have a command here that will actually go and grab the bank and the global namespace and fetch a balance from it. It'll respond. And so the last thing we need is we need ping to be a general purpose thing. It can't be just for ping anymore. So let's do that. Let's let's instead of calling it ping, let's call it send message. And let's give it a couple of excuse me, let's give it a couple of parameters. So let's give it an address, a command, and data. Actually, at this point, we don't need address. Will be kind of implied. So let's just give it address and data. And so with that, we'll give it command and data. And so with that, and we'll, instead of having hard-coded stuff here, we'll pass them in. And then we'll serialize the message, we'll send the message, and then we'll get a response and print it out. And so now down here we're gonna want a new method. Let's move this to the middle of the screen. If the CLI, so this is like in the command line arguments, right? So like if someone types what was it, my banknetcoin.py balance. This is what we want people to do. Be like my banknetcoin Alice, right? That would be cool. We could just get Alice's balance right from the command line. And so in order to do that, we're going to have to define another case here in our command line handler. And so that's what we want. Is we're going to want this is where it gets kind of hacky, though. It's like, well, how are we going to pull out Alice, right? This would be like this is the 0 argument, this is the 1 argument, this is the 2. It starts to feel kind of hacky, but we'll just go with it and then fix it later. So public key equals. So we'll grab the public key that they're the let's call it name, and then public key. And by the way, we could just pass some like the public key.toString here, but all of a sudden that gets like really ugly and it's hard to read on the command line. So as just a teaching utility, we're just going to be using names. And so we're going to look it up with that user public key of name, and then we're going to send a message with the command of balance. And then data would be the public key. We'll send that as the data. And here we're going to fix this. Okay, there we go. That looks like it should work. We will. Let's see. I'm sure there are bugs, but hey, let's try it. So kill the server, start it over again. And let's just run this. Python, mybankcoin.py, balance, Alice. Whoa, look at that. So it printed out, got a message, command is balance, data is this ECDSA verifying key, right? That's the public key. So that actually worked. It was able to send a serialized version of one of these public keys, just raw bytes over the internet, and then, not actually over the internet, just over between a couple ports on my computer, but then on the receiving side, it could reassemble these bytes into a Python verifying key, and it went and called this method, right? So it got here, and it called bank.fetchBalance, right? So that's up here. So then public key goes and calls fetch UTXO, and fetch UTXO now, remember, it doesn't have the toString hack, right? We remove that, and this is more proof that it works. This comparison works now with just the raw public keys. And so, like, one of these is the one that was created at this point, right? Bank.issue. And the other one, the one that came in as an argument, this was just like reassembled from bytes that came in over a socket. Which is it's pretty amazing that this actually works. And so then it fetches this list of UTXOs associated with Alice's public key, and then let's go back down. It got the balance, it summed up the balance, and sent it over, and you can see in the response, right? Command, balance response, data 1000, right? That's what we'd expect, wouldn't we? Because we issued her 1,000 coins. And what about Bob? Well, Bob's not so lucky. Oh, BOIB, right? So there you go. It blows up. We don't have any error handling, and we won't generally. But here's Bob's the other public key that we know about. His balance, unfortunately, is 0 because the bank doesn't like him, right? Which is a big problem with our bank. It can be, it can do whatever the hell it wants. But there we go. We now have an internet protocol that can handle fetching balances and stuff. So there's one more thing we're going to want to fix before we proceed. I want to get rid of this like janky sys.argv. Like for example, the next thing we're going to want to do is tx, right? If class or if the command is tx, right? And tx is going to take in more variables. You know, there's going to have a recipient, you're going to have a sender, and you're going to have an amount. And, you know, in the future, when we have multiple nodes running, like in a peer-to-peer network, you're going to have to say, well, which node do I want to send it to? It gets to be a bit of a mess. So instead of doing a bunch of this like really hacky shit, we're going to use something called docopt. Now, docopt is this guy here. If you go to the website try.docopt.org, you'll see this pretty little tool. This is like a really nice utility for writing command line arguments. Basically, what you do is you define the schema for like how you want your command line program to work, and you just copy this to the top of your file in like this raw format, and docopt can basically magically give you a command line utility. And so if you look at this example, navalfate.py, we will have like ship, like for example, if you run this with the ship argument, and then name must be guardian, and then it has move, which is defined somewhere here. Like it's kind of complicated, and we don't. This is what it is. So that's ship, move, and it's x coordinate, y coordinate, speed. So this is kind of what our transaction will look like, right? Like this will be like recipient. This will be sender or something. This will be amount. This will be like which node do we want to send it to? Which bank? You know, when we have multiple banks. And so this is kind of what we want. And so when you run it, let's see here. There we go. And so what it gives you is it gives you this really nice Python dictionary. For example, name. Where's name? Name is guardian. Look, that's cool. What is this? X. So if we look for X, it's 10, right? This one. Speed, it's like an optional argument, 20. That's great. So what we want is we want to make a BankNet version. So let's just on their website start copying it, and then when we're done, we'll copy it over to our program. So it'll be BankNet coin is the name. And for the usage, it'll be banknetcoin.py, and the you know, one of the things we want is well, we'll just copy that a couple times while we're at it. And so the first one we want is serve. Right? The second one, maybe this is a better way to do it. I'm fish out of water without my Vim here. And then the second one is ping, right? That's more like a testing method. It's not for real, but it's good to have. And so the next one is balance. And we want, for balance, we want a name, right? That's the convention, is when you have a positional argument, you put these whatever carets on the side. And so that's what we're going to do. We're going to call it name. And then lastly, we're going to have tx. And the other benefit here is, like, you know, when someone's using our command line, when we're using our command line tool, and if we enter in something that's incorrect, it'll print out this like helper screen, and it'll help us figure out where we went wrong. And so we want this .-h option, but for the rest of these we don't really need them for now. In the future we'll add a couple. But this looks like a good BankNet coin command line script. And so, like, if we said serve, let's see what it would give us. Right, everything's null, but serve is true. and this is JSON now. Like these are not, that's not Python anymore. That's JSON. And so, but in our Python, it'll be a Python dictionary. And so ping obviously would look similar, but like balance, let's see what that looks like. Yeah, so balance, name, Alice, balance, true. So that's really good. And so TX, Alice, gotta delete that. So there you go. But that was a good example, right? Like, right? I screwed up, and it says, "Hey, this is how you use it," right? It prints this really nice helper menu, and so that right there, you saw it help me figure out what the problem, that I messed up. And so there you go. TX now. TX is true. From is Alice. To is Bob. Name, remember, is from balance, so that's null still. And then amount is 100, but it's a string, so we'll have a little problem with cat. We'll have to remember to cast these to ints when they're ints. So now that we have that, let's just copy the whole thing. And so the way it works in Python is you just go to the top of your file and you do a triple quote, and a triple quote is like a multi-line string. And so what this will do is it'll send, like, I'll just show you. Actually, we'll say, I'll just comment that out. So you just print this dunder doc, this like global variable. And so, well, we'll need, that's weird. Yeah, so that's right. So it prints out this string, right? So this is, just to be clear that that's actually what's happening, right? So dunder doc, and then it prints out this string. It's just a string that becomes associated as like the document string for your file. This was generally intended as something that would be used more for documentation purposes, but what this docop project did is they found a clever way to hack that API and make it into a command line tool. And so it's really nice. You can like look at the top of a file and see how this file can be executed. And so instead of printing it, now what we want to do is we want to say we want to import docopt. And so this is where it's important to pip install. I've already done it. So and I think, yeah, you probably pip installed 2 at the beginning, but if you have any problems, just remember that we just added docopt as a dependency. So you might have to pip install. So from docopt, import docopt, and then at the bottom of the page you do let's just print it again. Right, we take that doc that we just got and we run it through docopt, and inside docopt it's probably going to be going and looking at, it's going to be looking at, excuse me, the sys.arg values that we saw earlier, and it's going to be basically parsing them according to doc, right? Which is pretty cool. And so we can still keep that, let's just keep that commented out, and now we'll just try running it like this, and I think it'll probably blow up, right? Yeah, so it prints us a usage message because, right, we didn't follow the directions. So if we say serve, remember this is just like on the website, right? Like it's printing us out the same thing, but instead of lowercase true, which is JSON, it's giving us uppercase true, which is a Python Boolean. And so, so yeah, that's what it would look like there. And we've already seen this, so I won't go over it again. But this is, so now it's working. And so if we go back here, we can just say we don't need to have command anymore. We can just say if if args of serve, right? Like it's false if it's not there, and it's true if it is. So this is kind of nice. We now are we're going to have a much more flexible system here. And then so if we look at back over here, name is just, this is how you would look that field up. And so we can just go over here, and instead of having to remember like what is, you know, which is at which place, we just say, well, you know, name is, and that's kind of much easier to remember and much more scalable. And so let's remove this print statement. And so, and what we can also do is let's move this into a main function, and then we can call it like this. So it's a little, you don't want this to get too bloated, so we'll just define our own main function and call it. So I think this should work. So look, if we hit serve, then it looks like it's serving. And let's grab Bob's balance. There we go. So now we have this function that is a little bit better to, we have a command line set up that's just going to scale with our solution. You know, when we have our whole Bitcoin thing in who knows how long it'll take, maybe we actually finish it in a week. When we have that, we'll be able to, you know, we'll have tons of different things, you know, that we want to be able, different messages we want our peer-to-peer, you know, like one of them could be checking up on the mempool. One of them could be submitting a transaction, right? Like, who knows? Maybe you could even submit a block. Who knows? And so, yeah, this is a big improvement. And so the last thing we want to do is we want to implement another command for transactions, right? We want our server to be able to handle transactions, right? That's the whole point of this bank and money, is that the bank needs to be able to update balances based on network messages, you know. So if Bob pays Alice, you know, Alice can get that transaction and say, okay, here, bank, you know, I got this transaction with a valid signature. Bob signed it. Why don't you validate this and update my balance, right? And so let's kind of start sketching it out. Let's we're going to leave some parts blank, but let's just start sketching it out. Excuse me. And so the first thing is, like, if command if command is equal to tx, let's just put ellipses. That's actually valid Python. It just means, like, don't do anything. And then here, let's say right, so that'll be this case. And so we're going to have, let's just copy this whole line because we're going to be grabbing some of those parameters. So I'll just paste it here. And so let's comment it out just so we know it's kind of for reference. And so we'll just put ellipses there too. So you know, what we're going to want to do is this is going to be kind of involved. We're going to have to construct a transaction, and then we're going to have to prepare a message and send it. But the constructing the transaction is going to be the hard part, and I'll give you a little help, or I won't make us. It's kind of, we've done that once, so I'm not going to make you do it again. And so yeah, those are basically, I think, the only two things we need. We need one on the server side, right? This is the one above, right? And then one on the client side here. So so let's do, the server side's easier, so let's do that one first. So I'll just scroll up. I can't get the transaction in the picture, so let's just go and look at it. So handle tx is what we're going to want to call, and that's actually pretty simple. All you have to do is pass it a transaction. And so what we want is we want to say right? Grab the data, and that's a transaction in this context, right? And you notice how data is different for every use case, right? So our protocol has this nice flexibility. We have this one parameter that can serve many different purposes depending on what the command is. And this is actually exactly how it works in Bitcoin. And so we have that transaction, then we're going to say, let's say, so now we usually ignore error handling in this class, but this time we're going to need it because without it, it just doesn't really make sense. And let's move this to the middle of the screen. So we're going to call bank.handle tx of tx, right? And then remember, this will blow up if anything goes wrong, right? And it'll blow up in a couple ways. Sometimes we'll have an assertion error, right, like this, if they're not spending a valid UTXO. And other times we'll have a ecdsa.keys.bad signature error, right, like we saw in the unit test earlier. And so in that case, we'll want to handle those and tell the user that something went wrong. So there's two different ways that this can blow up. So we'll just say except. We'll just handle any kind of exception that goes wrong. We'll just catch them all at once. And we'll just say, well, here, let's, if we succeed, we'll say self.respond of, and this is we just tack response at the end if it's a response to a command. And actually, we'll just have the data be accepted or rejected. How about that? So that looks good. So let's copy that and put it down here. And instead of accepted, we'll say, if it encountered an exception, we'll just say rejected. In a real application, we'd want to tell them why. But like, YOLO, we're just doing a thing for fun. And anytime something goes wrong, we probably know what went wrong. And so, and we're going to delete a lot of this code. Well, we'll delete some of it. But so that should pretty much handle the server side of things. Yeah, so now we just need to do the client side, right? And so this is where it's going to get a little hairy, right? We're going to say, well, first things first, let's just grab the relevant keys from our CLI arguments. So the first thing we want to do is we want to, there's going to be this from key, and we're going to want to look up a private key there. And this is also kind of hand wavy. Like obviously, it's kind of weird that you can look up private keys like this, but since this is all just like a simulation, that's okay. 2 is going to look up public keys, right? Because that's what you need for a recipient. And then amount is just going to cast it to an integer, which is really important because doc_opt by default is going to give us a string. So I'm just going to type this out and follow along. So center private key is just going to take whatever name was in from, grab that name, and run it through user private key, which I think we might still need to import, yeah. Right, and that's actually still over here, user private key, right, or user private key here. And so user center private key, and we're going to need, so we'll grab the public key of the recipient, and we'll grab the amount. That all looks pretty good. And then so this is where it gets a little hairy. Like we're going to need to we're going to need to fetch the sender balance, and we're going to need that. This is actually going to be a network message, right? Actually, what we're going to want to do is we're going to want to fetch their UTXOs, right? Whatever is unspent transaction output, we're going to want to fetch those, because when we prepare our new transaction, we're going to need to know which outputs this private key controls, and we're going to use those as to construct the TX ins of this new transaction. So that's like a note to self. Then we're going to say, like, let's prepare the transaction. And then lastly, send it to the bank. And we can make some capitalizations, and we can delete that now that we've kind of grabbed all the content we need. And so fetch sender UTXOs is actually going to have to be another method, and it's basically going to be exactly the same as this one. So we can copy that and paste it, and so it's going to take let's call it UTXOs, and it's going to take a public key as the data, and it's going to call fetch UTXO. Actually, we'll just, in the actual solution to this, I standardized the use of like UTXO, UTXOs, UTXO set. Like I kind of use those, I use a UTXO for everything here, whether it's singular or plural, and that's kind of confusing. So I'll just keep this convention, but if you look at the solution, you'll see that the words here are going to change after this lesson, but I'm just going to go with what we've had for now. And so fetch UTXO, and then we'll send this response, right? And so over here, we're going to have to get that. So we're going to want to send a message for UTXO, right? We're sending a first message trying to figure out what outputs we can spend, right? And so we're going to need the sender public key, right? And so we don't actually have that yet. So let's say you can grab it by the private key.get verifying key, right? So we'll grab the sender public key, and we'll use that to fetch their UTXOs. And so UTXO response is equal to that, and the data is the actual UTXO, the list of UTXOs themselves. And so in order to prepare the transaction, I'm gonna give you a helper function. And so it's going to be called prepare simple tx, and that's going to exist in the utils.py folder or file. And so here it is. It's pretty simple. I'll just walk you through it. I'm not going to make you type all this out. So it takes a list of UTXOs, the sender's private key, the recipient's public key, and the amount, right? And so what we do is we go and we iterate through the TX outs, the UTXOs, and we just append them until we reach a sum of TX in amounts that exceed the argument amount, right? So we're just going to like add in UTXOs that we're going to spend, and we're going to convert them into TX ins, right? We grab the TX ID, the index, but they don't have signatures, right? Because we need to sign them at the very end, right? But now our signature scheme depends on having the UTXOs set, right? You know, if you go up here to the top of the file, remember, this is going to take in the out point, which is associated with the TX in, but it's also going to take in the list of TX outs, right? So we can't sign until we've prepared the entire transaction. And that kind of makes sense, right? If you're going to assign some input, you want to know everything about where that input's going. And so this kind of makes sense. And so we're going to prepare the list of TX ins. We're going to assert that the sum is greater than or equal to the amount, right? Because if it's not, we're like, it's, you know, game over. and that would happen if like this is an empty list. That would happen. So then we're going to construct the TX outs, right? The first one is going to go to the recipient for the amount. The second one is going to go to the sender for the change, where change is just the sum of everything minus the amount the sum of all the inputs minus the amount we're spending, right? And then lastly, we prepare a transaction, and then we sign every input using the sender private key. And in this scenario, there's only one. Well, I guess there could be more than one input, but they're all associated with the same private key. And then we return the transaction. So, you know, it'd be a lot of typing. I'm glad I don't have to type that myself right now. So, so let's just call that. So the first thing we have is, can we fit all this on one line? Let's just do, well, we can go like this. So we're going to have UTXO first, right? And then sender private key, then recipient public key, and then amount. And we can maybe go like that. That looks a little better. And so, so yeah, that'll actually prepare a transaction. It won't do anything with the transaction, but it'll prepare it. And then so we can hop down to our next step and say, actually, send message does not have an address at this point, right? So in the future it'll have one. But so yeah, just send a TX message with that transaction as the input, and then let's print a response, right? And so now I think, right? Let's just kind of go over everything. So we have UTXO, data, fetch public key, response, balance. Well, it's not a logical error, but it's an error. And so yeah, that looks pretty good. So if we go and call the thing like this, you know, TX Alice Bob amount 10 or something, I think this should probably work. So let's go over to our terminal, clear the input, run the server, good, no syntax errors. Let's say TX, and we're going to send from Alice, right? Because right now she's the only one with any coins. So let's see what happens. Send public key. So that's a typo. Sender public key. And so it looks like I forgot to send so the UTXO response yeah, so we have another little error here. We're going to previously send message was only printing things because we weren't actually doing anything with our outputs. But now we'll just leave the print in there, but let's return the message, right? Because we actually need the output now that we're doing something with this UTXO. It's not sufficient to just print it. Okay, so after some last minute debugging, let's see what happens when we run the code. Actually, let me just show you. So yeah, there's an import problem. I had to import some of these things in order to send the prepare simple transaction. So I'll fix all this. You won't have to deal with any of this yourself, but I'm just kind of doing this on the fly. So I had some bugs and sorted them out, and they were all in this little utils.py, which you can safely ignore. And so let's run the server, and let's run Python mybanknetcoin.py Alice Bob 10, right? Alice sending 10 to Bob. And boom, look at that. So the server received not only one, but two commands, right? The first one is UTXO, looking up what Alice had available to spend when she executes her transaction to Bob. And actually what we could also do here is, well, I'll do that next. And so after it fetches UTXO, the client was able to prepare a transaction, send it to the server. The server executed that transaction, validated it, and sent back an accepted message. And so look at that. We were able to prepare, and a client was able to prepare and send a transaction to our server completely across a raw internet protocol that would work if they were on other sides of the planet. And let's see what happens if we check Alice's balance. Look at that, 990. Remember, she started with 1,000, right? Right, we issued her 1,000, and then she just sent 10 to Bob, and so her balance is now 990. What do you think Bob's balance is going to be? Bob's balance is 10. Look, the book's balance, it all equals what we issued to begin with. And so there you go. We have a working internet protocol for our stupid bank coin. And in the next section here, and right up next, we're gonna try to split the bank up into multiple different parties. So let's jump right back into the slides here. So this is where we left off, right? BankNet coin. So sharing the power. This is what we want to do. We want to BankNet coin. The bank controls 100% of everything. That sucks. They're going to abuse it. That's like the whole reason for Bitcoin is you don't want these. You don't want these sort of like monopolistic, institutions protected by regulation choosing what your money is. That's really dangerous. And so the bank will abuse their power, will help us to stop it. We need a mechanism to accomplish the issuance and transaction validation that the bank does, but we want to split it across multiple entities, right? And that's what Bitcoin does, really. This is really a deep question in Bitcoin, but like, broadly speaking, these same tasks are accomplished via miners, and miners prevent double spends, but also by full nodes. If you have your own economic full node running a copy of the Bitcoin software, that is your canonical version of validation. Whatever that sucker says is what you believe. And then issuance is by Bitcoin's mining subsidy and the decaying subsidy the subsidy that goes to zero over time. And so here's the scheme we're going to try to implement in the second half of this class. We're going to kind of try to transform BankCoin, the BankCoin server, into a network of BankCoin servers. We're going to create n different banks, all of whom agree on the validation rules, right? They're all going to be running the same piece of software. Each bank is given a numerical ID, right? Bank 0, Bank 1, Bank 2. And in our case, we're only going to have 3 banks at a time, but you could have like 50 banks. And if you're looking for a cryptocurrency that looks like this, this is basically EOS, right? Like EOS has 17 banks, and they're the ones that do all this stuff. So like, in a sense, this next thing is going to be an implementation of EOS, which doesn't speak so highly of EOS, right? If we're able to do it in our pathetic little class here already, it's not so good for EOS. So these banks alternate nominating a set of transactions every M minutes, right? So in our example, it'll be every like 10 seconds or something, just so you don't have to wait around, maybe like 3 seconds. So like they'll just alternate, like basically like if the however long the blockchain is, it's however long the list of blocks is, that will determine whose turn it is. And so the non-nominating blocks will verify whatever block was submitted by the nominating bank the non-nominating banks will verify blocks submitted by the nominating bank. And what this scheme accomplishes is it spreads out the power a little better, right? You have a number of different bank type entities that might not like each other, are kind of competitive with each other. And so hopefully that kind of Mexican standoff scenario will actually be a little better, right? It's an oligopoly instead of a monopoly. And so here we go. This is what we've all been waiting for, right? BlockCoin, magic internet money. And if you're wondering, the reason why we call it BlockCoin is blocks are going to be the unit that allows these different banks to pass along transactions to each other, right? When we say nominate a set of transactions, that's a block. So in order to implement BlockCoin, we need to have some sort of environment where we can run multiple servers at once and they can talk to each other. One way we could do it is just with basic shell scripts and have them running on different ports on our own computer. But there's actually a better option, and that's Docker. Docker is it's a huge ecosystem of software that works similarly to like virtual environments or VMs. They allow you to take a little bit of code and spin up like a small self-contained kind of an instance of a subset of Linux that will run this piece of code, and it just does that one thing, but then it can talk to other containers. These things are called containers, and this fits in really well with our project. We can run each instance of our BlockCoin server in one of these little containers, and they can all talk to each other, you know, going around every 10 seconds, nominating a block and verifying the blocks they receive. And then in the future, we can run a full peer-to-peer network like Bitcoin simulated within these Docker containers. And there's a lot of tooling in the Docker ecosystem that makes this sort of stuff easy to build. So what we're going to do first is we're going to make like a small little prototype, a series of little prototypes that do this sort of thing, and then we're going to port them back to what was Banknet coin, which will become BlockCoin in the second half of this second half of the video. So let's get started. So you want to open a couple files: experiment/pingpong.py. This is basically the same thing we just built. Then you're going to want to open experiment/docker file. And so this is the instructions. These are the instructions that tell Docker how to configure the container that will hold and run our eventually our BlockCoin server. But right now it's just going to run pingpong.py. And lastly, this is a Docker Compose file. As you see, you can define a number of services, and basically every one of these services for us is going to be practically the same. It's just and it has a couple nice things. It has a mapping of the ports. So like this is the port that it's running on within the container. This is the port that it'll be accessible by outside of the container. And these are like some environmental variables. So like we'll tell them what the names of their peers are, and we'll tell them what their ID is. And you know, so each now that I think of it, we could probably infer peers based on what the ID is, but whatever. We'll just go with this. And so that's really what we want to do. Is we want to we're going to have this little network where each one of these little nodes will be able to talk to each other. And so yeah, this is basically sufficient to spin up a little constellation of ping pong servers, which aren't any good. There's no reason why you do that, but this is a place to start. And so I'm not going to have you type these out by hand, because really no one types out Docker files. Really, most of it's just copy and paste. And similarly, kind of with Docker Compose, you know, you're usually looking for examples of something you want to do, and you basically go and copy and paste parts of what other people have done previously. So this is just the kind of instructions to spin up this little fleet of ping pong servers. So if we go over to our terminal, excuse me, and you type, so first off, you're going to need to install Docker and Docker Compose. Or maybe, you know, in Slack you can ask questions about this if you can't figure it out. But in general, just Google it. You know, I'm not going to walk you through that. And so what you're going to want to do is you're going to want to type Docker Compose -- build. This is what we're going to do every time. And Docker Compose up, sorry. And this will sort of spin up this actually builds the server, and you'll be able to see these different commands are straight from the Docker file. And then this is the Docker Compose logic starting. These are, you know, spinning up the different nodes. And so now it looks like it's all running. We don't have any logging in our app to tell us when it started or not, which is not so great. But what we can do is we can say, you know, telnet. If you recall, you know, here are where they'll be accessible: 1000, 1001, 1002. And so if we do that, we should be able to say ping, and there we did get a pong. So it is working. We're able to talk to these little Docker containers because Docker Compose allows us to have this neat file that'll sort of describe how we want the the containers to be networked to the outside world. But one thing you'll notice is that there should have been some sort of logging over here, and there wasn't. And so that's going to be our first alteration. And I'm not going to have you type it out because it's basically another copy and paste job. But if you go and switch this file name to ping pong docker, and you're going to have to change it here too, which is what actually copies over the file to the local system. And if you go over here, there it is. And so it's basically the same thing, but I just add this one little section which defines a logger. A logger is just like it's like a more reliable way to generate print statements and to put the output that we've so far been printing into log files and to format it a little better, right? So this one will say, it'll lead with what time it was happening, what the level of the log was, like was it an error, was it just a debug statement or warning, and then what the actual message was. And so we won't go into it too far, but loggers are, once you start like writing an app that's kind of deployed, and in a sense these are now deployed, they're running within a Docker container on our own machine, they're deployed to a like local setup, it's better to start using logging. So where we used to say print, now we say logger.info. And so if we go over here and start everything over, let's clear out the input, and if we run everything, now if we telnet in, we get some logging in output, right? Received, ping, sent, pong. Wonderful. When it happened is a little excessive, but whatever. And what what level it was, whether it was info or warning or error, So if you actually deploy this, sometimes you want to just search your logs only for errors, for example. That's usually what you're most interested in. And so yeah, there we go. That's kind of a simple. That's a simple sort of what would you say? It's like an ecosystem of these. It's a network, really. It's a network of these ping servers, but they don't have any really ability to talk to each other. And even if they did, they don't really have anything to say so far. So if you go and recall how our BlockCoin is going to work, right? Like we have this idea where each bank will have an ID, and they'll basically alternate nominating blocks. And so we're going to make a little prototype of that, and instead of alternating nominating, instead of sending your peers blocks, we'll just send them pings. So we'll sort of go around the circle with our nodes, and each node will go and ping their peers, and then they'll wait a couple seconds, and then the next node will ping its peers, and we'll just go around the circle, because that's basically the logic we want to implement it. But if we implement it in this sort of simpler ping environment, I think it'll probably go fast and it'll make more sense. Okay, so let's start implementing this. So the first thing we need to do is copy the ping pong docker file and make a new file that we can start building from. So copy ping pong docker. The hell should we call this? My alternating.py. I have the solution example is called alternating.py, so we'll just call it that. And so what we're gonna want to do here is go over here and open up my alternating.py and leave the Docker compose and the Docker file open on the side if you like, just as a reference. And so the first thing we're going to want to be able to do is we're going to want to be able to have our peer, like when we start this up, we're going to want our peers to be able to go ping all of their peers, right? Because that's what we're going to want to do. We really need to do two things. We need to have one of our a server go and ping all their peers, and we need to be able to schedule that ping, let's say a certain number of seconds in advance, like from now, maybe 1 second from now, depending on some condition. And so let's write the first one, the ping peers. And so what we're going to want to do is we're just going to want to somehow get the peer host names, and hint, we'll get them from this variable here. We pass it in as an environmental argument, right? And so node 1 is this guy, node 2 is this guy. So we'll have to grab that somehow, but for now let's just assume we have that as a variable. So we'll iterate over all these host names and then ping them. And ping only takes a host name, it doesn't take a port, because every one of our Docker containers is running on, runs this program on the same port. So all you need, the only thing that's going to change is the host name, and these are the host names. The Docker networking magic allows you to use these as host names instead of IP addresses, which is kind of magical. So yeah, that should work. And what we're going to want to do is we need to define this. We need to grab this somehow. So let's kind of go up to the top of our file here where we have all that kind of stuff. And I'll just show you how to do it. We'll just grab the variables from I'll just show you. This is actually called a set comprehension. Well, we'll do a list comprehension. That's simpler. Actually, let's, just to make this a little simpler, we can yeah, I think that actually works. So we just grab this os.environ is how in Python you access the environmental variables. And remember, this Docker will pass this in. It'll be called peers. It'll pass this string in. And so we're just going to read that from our environment and split it on the comma, right? And in order to do this, we need to import OS. Now, in order to call this method, we're going to want to make sure our peers have already started up, because they'll start up in order, and you don't want the first one to go and ping its peers and they're not awake yet. So what we're going to do is we're going to use another really heavy hitting or a really widely used module called threading, and it has this little magical thing called it has a timer object which will allow you to execute some code in a certain number of seconds in the future. And so what we're going to do is we're going to write another function here. And we're going to say actually, I think you can probably and in order to do this, we're going to need to pass in the host names as we're going to need to pass them into the ping function. So let's do that. Right, so we're no longer just going to be using a hard-coded address. Address equals where port is defined at the top of the file here. Let's just call that adder just so we don't, we have a little bit of collision with this function here, so let's just avoid that. So now we have that, and now we just need to call this somewhere. So let's just call schedule pings when we spin up our server. You need to go and change the names in your Docker file. Right, you need to tell it which file we want to run, what we want our server to run. And so now when we run it, we'll see, boom, about 1 second after it spun up, all of our nodes went and pinged their neighbors. And so it's kind of a barrage of pings, and I won't attempt to decode it right now. Although it might make yeah, I mean, it all happened at once, so it's going to be hard to decode this, but it kind of makes sense. It looks like they're participating equally. And so what we want to do is figure out a way to have people have the nodes alternate how they do this. So to do that, we just need one global variable. Let's call it current. And we'll start it at 0. That's like the ID of the lowest ID of our peers. Remember, we have this ID over here that's defined. And so also in the top of our file where we get the sort of our global variables, let's grab the ID from the environment. And so what we're going to do is we're going to start at 0, and we're just going to, every couple seconds we're going to increment it and then check whose ID is that number, and we'll have them ping their peers. And when we're incrementing, we'll go up to 2 and then go back to 0. So we'll use modular arithmetic to just go between 0, 1, 2, 0, 1, 2 for the current ID, and that the node with that ID as their as this global variable, that they're the one who will go and send the ping message to their peers. So I know this seems trivial, and please bear with me, but this is like getting a handle on this is going to help. So what we want is here in this schedule ping, we'll just say like actually I think we'll need to specify it's global because we're changing it here. So every time we do schedule pings, we're going to increment current and then mod it by 3. So this is how we're going to go just 0, 1, 2, 0, 1, 2, 0, 1, 2. And then we're not going to call threading. We're not going to schedule a ping every time. We're only going to schedule it if this node's ID is the one whose turn it is. That makes sense? And so now we need to, we don't want to just schedule it when the server is first run. We also want to schedule it every time we receive a new message, right? So right, we'll just call it, and it'll handle the incrementing, and then if you need to if it's their turn, it'll handle the scheduling the ping. And we also need to do it when we're the ones pinging, if that makes sense, right? Because when we're the one that sends a ping out, we'll still need to increment to the next person, to the next node, because we won't be receiving a message ourselves. And it looks like I had a little. Oops! Looks like I had a little. I said schedule ping, and I needed schedule pings. So yeah, let's add one more logging statement here. And so if you hit enter here once, every second or so, you can kind of separate the messages. And so here's a good one where you can kind of see what's going on. So node 2 sends ping, and then node 2 receives a pong, and it looks like node 1 was the one who sent or received the ping and sent the pong, right? And then the same thing here happens between node 2 and node 1. So you can kind of see how it's going here. But one thing it'd be nice to have just a little more logging about where the messages are coming from. And so I have, if you just, it's really a tedious change, but if you just change these, the files here to or just alternating.py, this has one little change that basically grabs our peers' addresses and does a little regex formula to grab their just their host name, so you can tell a little bit easier who you're talking to. And so this isn't terribly important, and I'm not even sure it'll work on your guys' computer. It just works on my system. But this is a little, just as a demo. So I'll just kill the script there. So here we go. Node 1 says sent a ping to node 2, right? Then node 2 says received ping from node 1. And then node 1 says received pong from node 2. And node 2 says sent pong to node 1. So you can tell that this third and this fourth message are out of order. So the logging is not perfectly like linear. And so that's a little odd. But you can really get a good sense of what's going on here and how these different nodes in our little network are communicating. And we really accomplished sort of like an somewhat interesting networking feat here to have this little network of nodes talking to each other. And so the next step is let's try to apply this little prototype that we just made in order to finish BlockCoin, in order to make it so that our bank netcoin can be split into many different servers, and these servers can all talk to each other and in a rotating fashion share the block nomination responsibilities. Okay, so let's hop back to our terminal in the root directory of our project, and let's create a copy of the file we just. Let's create a copy of BankNetCoin and put it in my BlockCoin.py. And so this is where we're going to implement BlockCoin as a sort of an evolution on the BankNetCoin we just made. And so if we hop back over to our terminal, let's have my BankCoin open and BlockCoinTests.py open. And BlockCoin tests are going to work similar to last time. It's just a couple of test cases that we want our system to work with. And it's a little more complicated this time, so hopefully I don't get lost in all the complications as we go through it. But just to see where we're at, let's just try to run. Let's try to run the tests, and looky there, it's just completely incompatible. We added this new attribute to banks called ID, and we also gave them private keys that aren't always the same. I think last time there was a private key, but it was already like hard coded. And so now we have some, just because they're different, right? Every bank's gonna have a different ID, a different private key. So it's just a lot's gonna change here. So first of all, let's update the bank's constructor method so that we can actually run the tests and get a little bit better understanding of what's failing. So the way it's going to change is this time the bank is going to have, each bank is going to have an ID and a private key. And previously we only had the UTXO set attribute on the bank, and you know, I was mentioning there was kind of a bank private key, but it was sort of like stored elsewhere, right? It wasn't actually on the bank class itself. So in addition to the UTXO set, we're going to have we're going to save the ID, save the private key, and we're going to just keep every block we get. Like, you know, I kind of made a point the other day in the last lesson that, you know, the UTXO set was sufficient. But let's like follow Bitcoin's example, and let's hold the blocks and the cache of unspent transactions. Let's just keep track of both of them. And so self.blocks will just be equal to just an empty list. This is a empty dictionary. And so then we also want self.mempool. So these are the transactions that haven't gone into a block yet, right? These are kind of all the clumps, the sets of transactions we've seen. These are all the unspent outputs. These are whatever someone has, you know, in our peer-to-peer in our networking protocol from last time, remember you had that TX method, right? If this one. So like if someone sends us one of these transactions in this new version of our protocol, handle transaction will add it to the mempool. That's the stuff that we're waiting to submit into a future block. Oh yeah, so we have one other thing we need to do. We had this sort of like a global bank instance here, remember from last time? And so what we should do there is say let's just make it into none, and like let's make a little to do. We have to instantiate a bank here later. And so now if we run it, okay, cool. So we have a couple different errors. And so I think this is a good one to start with, right? So like what our first test case, let's just look over here, test blocks. So this is what we want to do. We're instantiating a bank, right? Then we're making a block with no transactions, just an empty list of transactions, and we're just checking if the mechanics work. And basically how it works is every block is going to be signed by the bank whose turn it is to submit the block. And so when the bank handles, when a different bank handles the transaction, they'll go look around and check if the right bank gave the signature. And then we'll just check whether the list actually that's not even right. Whether the list of transactions is correct. So now if we so what we need to do next is we need to actually implement block. Okay, so let's start writing the block class. We'll just start writing the constructor, and then the other methods that the block class will have we'll implement later as we need them. And so this is what it's going to look like. Every block it's just a list of transactions. Fundamentally, that's what it is. Next is a timestamp of when the block was created. Strictly speaking, we don't really need that, but I think it just makes sense to include it for sanity's sake. Like if we were to write a little bit more, like our code in this lesson is not going to be checking this timestamp, but if you know. You probably would want to check it, and we'll discuss that later. And lastly is the signature, and this is the signature of the bank whose turn it is to issue the block. And that's the idea, right? The banks will alternate submitting blocks to their kind of shared blockchain, and in order to prove that the correct bank was the one who put together that list of blocks and submitted it and nominated it, they're going to have to sign it with using their private key, right? And everybody will know the public key of each bank, and so that way we'll be able to verify that these blocks were legitimately created and not forged. And so we're going to create, if the timestamp is none, we're going to just set it to the current time. And that's just time.time, and we're going to need to import time. And so and let's this sort of should go after the transactions. They should all be together, right? And the block will come after them. Okay, that's good. So it looks correct. So as always, let's run back over to our unit tests and run them. See if, so this is where we couldn't instantiate a block last time. Let's see if we can get a little further than that. Celt. That won't do, will it? Okay, so we got past block instantiation. Now we get to block.sign. Obviously, we haven't implemented that yet, so let's go implement it. So we need a sign method. And we're going to need a, much like we were using this spend message, remember, for when we sign the inputs of a transaction, right? We create a spend message. We're going to have the same kind of a message. It's just like the, I'm not going to give it any sort of name. It's like the block nomination message or something. It's just whatever. It's just a way to for the, you know, to encode all the relevant data inside the block that the block producer, the bank, is committing to when they sign it, right? And so that's basically the transactions and the timestamp. And so if we implement that, just put it above because that's kind of the order they go in. And we use the property decorator so it'll look like a static attribute, not a method, just because I think it looks a little cleaner. We'll just say data is equal to and the reason why, you know, you might be thinking, well, could we just say self here? Could it sign self? And the reason why we can't just sign and serialize the block itself is because when you sign it the first time, signature is going to be none, right? But then when someone verifies this, the signature will be filled in, and so like you have to sort of remove this from the commitment because this is sort of like a you know, it changes when a block is first created before it's signed. This is missing, and so but then after it's created, it's there. So if you include this in the serialization of that becomes the message that's signed, it would look different to the creator of the block and to the verifier of the block. So you just have to remove that one variable element here of the block and just include the timestamp of the transactions, right? And we could do this in any data structure we want. Like we could use a set, you know, we could use a tuple. It doesn't matter. It just matters that it's consistent, right? So we'll just use a list because that's the simplest one. And in this class, we're striving to, you know, have simple code but cover complex ideas. So we never try to do too much, you know, fancy coding. And so that should work. So self.signature equals private key.sign. We have self.message. Cool. Let's see if we can get past that line of code. Okay, cool. That was the first one that stuck us. Then we got to block.sign. Now we got to bank.handle block. And so this is really the key code for this lesson is what is the bank going to do when it gets a block, right? How is it going to translate a new, how is it going to update these three fields, right, when it sees a new block? And in plain English, right, if the block is valid, it's going to want to append it here to the end. If a block is valid, it's going to want to take every transaction that is contained within the block and update the UTXO based on that transaction using the same logic we had last time, right? We already have a set. We already have a method that can update the UTXO set based on an observed transaction, right? So that's pretty much the solved problem. And lastly is mempool, right? When we see a new transaction, we're gonna want to remove it from the mempool if it was in the mempool. So those are a couple things we're going to want to cover here. So let's get started. So handle block, that should probably go, you know, let's stick that below handle transaction. And just as like a little more context, right? Like later on, we're going to want to write, you know, something like this, like, right? So we're going to have, you know, right? Like that's what that'll look like. And I'm just going to leave that in there just so you kind of get a sense of why we're doing this. Like this is what we want to be able to do when we get a network message saying like here's a block, this is when this code is going to be run. So we'll just start with I'll just write some comments and then we'll fill in the code. So we're going to verify the signature of height is greater than 0. The first transaction in our scheme will have no signature. It'll be like the Genesis transaction in Bitcoin. Verify the bank signature, right? We want to make sure that it's being the block was created by who we expect it to be created by. Verify every transaction. That's pretty obvious. Update the UTXO set. That's just the unspent transaction outputs. And just say update the blocks. Let's just save the block to our database. And let's there's one thing I'm following along with, like a previous version of this. Like I'm not just doing this all from memory. I'm looking at another screen with like the kind of the answer here. And there's one thing that I don't have there, and that's, let's just say clean the mempool. You know, if this transaction was in our mempool, let's remove it. Okay, so that looks pretty good. That's like everything we'd want to do, right? I can't think of anything else we'd want to do. And schedule next block here, this might sound a little confusing. That's like basically what we were doing in our ping pong thing, where we would like schedule the next ping pong out a couple seconds, right? Like this is how it's going to work. Every time we see a block, we're going to check, hey, am I the next person am I the next in line to schedule a block? And if so, we're going to use that threading.timer API to like schedule the submission of another block. And so that looks good. So let's start actually filling it in. So we don't have like an actual height parameter anywhere. We just calculate it based on how long self.blocks is. And here's some stuff we're going to need to fill in. Okay, so this whole thing already exists. We know how that works. Now, there's two things here that we don't have yet. Bank public key is like a function. We have this identities file, which is just like some hacks to, you know, grab the relevant parameters we need. So bank public key works similar to this user public key thing we used earlier. It acts like it's like a public database of public keys. And so it just takes a bank ID, right? Remember in our Docker compose file, this is now the one for the actual BlockCoin. It'll look exactly the same as our ping pong server. Remember, everyone will have a bank ID. Every one of our instances of this bank server will have their own ID, right? And they increase numerically, and so we just look up. This is just a function that can look up a public key, like a deterministic way of looking up a public key based on that ID. So it's a bit of a hack, but it works. And so we need to import that. So we also need next ID. And so next ID is basically the function that'll say that'll determine whose turn is it to issue a block. And the way it'll work, I'll just put these. The way it works is just like you get the length of the blockchain, and then you mod it by the number of producers we have. And that'll just like it'll give us a number, in our case 0, 1, or 3 or 0, 1, or 2 every time. So and so this num banks is not defined, and we'll just put that we'll just say, let's just hard code it as 3. There's probably a better way of doing that. Like we could just like split this and see how many of them there are and add 1, but it's just kind of like, for our case, let's just say 3. It's just simpler. So where are we? So next ID. Next ID looks like it's done, right? So that makes sense, right? Like, so when our blockchain has so we'll start with 1 block that we'll have like an airdrop, basically. That's how this coin will work. And so after the airdrop, the length of self.blocks will be 1, and then mod 3 is 1, right? If you don't know what I mean, if you don't know what this means, Google it. Google modular arithmetic. It's like a clock, right? So after 12 hours, you just divide it by 12 and take the remainder, like that. It's like how clock arithmetic works. So you know, and so when you add 1 more block, then all of a sudden it'll be 2. 2 mod 3 is 2, but then once you get 1 more, you'll have 3, and 3 mod 3 is 0, right? You take the remainder after dividing by 3, and that's 0. And so now it'll be the 0 node's turn, right? So it'll just go, like, it'll be this guy's turn, then it'll be this guy's turn, or sorry, the first one will be this guy's turn, right? Because we start with 1 block, then it'll be this guy's turn, then it'll be this guy's turn, and then we just go around. And this is a pretty simple way of doing it, just modding the, you know, we don't need an extra parameter. We just take the length of the blocks and mod it by 3. So that's pretty good. I think now we have bank public key, we have self.nextID, and this is good. So we've accomplished this first block of our handle block code. And so for every transaction, this one's also going to be pretty simple. We just iterate over the transactions. And we validate transaction just like we used to do. You know, there's nothing in this new scheme that will change that. It's just like look it up in the UTXO and, you know, do that whole thing. And so, but we're gonna validate every transaction before we do any updates to the, you know, you don't want to do like, you don't want to do that here, right? Because the last transaction may be invalid. So you don't want to make any changes to the UTXO set or anything until we know they're all good. So here, once we've gotten them all, we'll do a for loop again. And we'll now update the UTXO set. So like at this point, we know the block is good. Like this is verification, and this is like updating stuff. And so I actually haven't written this one yet. This is like, okay, so I'm just actually going to leave this as homework. There's no like really simple way to do this, at least that I can see, because we can't just say like, you know, like we can't just remove like self dot. I think remove is a valid method. We can't just do this because remember our transaction classes don't have this dunder EQ on them. Remember? It doesn't have one of these. So like this actually, I don't want to test here because I also don't have a unit test with this. Sorry, but this actually won't work. At least I don't think it will work because we don't have the right, like, we can't just directly compare these different you know, instances of TX of transactions. So I'm gonna assign this as homework. Like, do this. This isn't included in a unit test, but this is one other thing we should do to make this completely correct. In our examples, like the rest of the thing will work, but if we had, yeah, we'll touch on this later. But this is homework. You do that. I've done enough coding. And so lastly here we want to say, we want to append it to the blocks, right? That's pretty simple. And then schedule next block. And we'll just add this at the bottom. All right, let's say to do. And so we'll just say this just basically means it does nothing. And so we'll implement this once we finish the unit test and actually start making this work in our network scenario. So let's run the unit test here. Handle block, of course, typo. Another typo. So that I just left a colon. I missed a colon there, and then this is supposed to be self.blocks. And then this needs a self. Okay, that's pretty good. So it actually looks like we got one test to pass. This now, yeah, this works. So since we have the bank, we actually implemented this block signature stuff. So if you submit a block with a bad bank signature, this test does raise an error, and so now this test passes. We have one passing test, at least that I can see. Yeah, bad TX, test airdrop, and test UTXO all fail, but test blocks works. So hooray, we're 1 for 4. So let's move down to test bad TX. And so what happens here is we update the signature afterwards and put in just a signature of the word bad, right, which is like not going to be a good signature. And so it should raise a bad signature error, but it doesn't. And so actually, I think the problem is that it never gets that far. It doesn't get to bank.airdrop. Okay, so let's implement airdrop. This is just like an ability to create a first block from a single transaction that sort of like sets the initial balances for everyone in our population of users. Our population of users for this little toy is just Alice and Bob. And so this is not like maybe, you'd want to think this through a little bit better if you were doing this for real, obviously. But it's good for our little toy scenario because it just allows us to spin up a world with some identities and some balances. So let's implement this. And so we basically need to do 3 things. And right, we can't use handle block because unless like we heavily modify it, because and actually now that we're going to have a separate thing, we could actually just remove that. We just always want to verify bank signature, right? We don't want to check. We don't need to check if it's like we're going to do the first block separately. So down here, so we can just remove that condition. And the reason why we can't use this is we don't want to validate the transactions, right? Like if you look at the these, these are not valid transactions. These are creating money out of thin air, right? There are no TX ins, there's TX outs, right? This is like totally illegal, but we're going to allow it in the first block. And the reason is like this would be something the bank does arbitrarily based on whoever they want to give money to, right? Or the banks together as a, they'd all get together and decide who gets the, maybe everyone gets the equal amount. So we want to check we want to check we want to check that there are no blocks. And then we basically want to just do these. We want to update the UTXO set. And then we want to append the block. It's just going to have one transaction. And we're just going to want to append that to our blockchain. And that's all we need. There's nothing else we really need to do. So yeah, now hopefully that gets us past our unit test. Let's just clear the output. And so surprisingly enough, now all our unit tests pass. So we've basically done everything to get the basic logic of this to work. We still have some work to do, right? We haven't implemented schedule next block, and we haven't. But this is all like now stuff for, or getting this to actually run within Docker as like sort of a self-contained like environment, right? And so let's start doing that. Okay, so I hope you're still with me. We're going to start integrating this BlockCoin server with the Docker ecosystem that we had last time. So just as I'll just pull up, what was it, alternating.py. This was like kind of the last thing we ended up doing. So I'll just have this kind of open over here. The most important thing is the mechanics here. This schedule ping is going to become schedule next block, right? And this stuff is a little confusing, but like this is our kind of our synchronization mechanism in lieu of proof of work, right? Proof of work next time is going to be what replaces all this stuff, and the next coin we're going to do is going to be called POW coin, for proof of work coin. So let's start implementing this. So we need schedule next block, and so all that will do is say if it's our turn, we'll just call this exact same, we don't actually need that anymore. And let's say for here, let's say, let's make a block time variable. So block time is going to be number of seconds between blocks. Okay, so and instead of ping peers, we're going to call self dot, let's call it self dot submit block. And so what submit block is going to do, it's going to create our next block from our mempool and send it to all our peers. So we're going to need a make block method. And a submit block method, which will call make block and actually create it. So this will be, right? So the first thing we'll do is create a block, and the block will come from the mempool. So we're going to take deep copy of the mempool. This is just a list of transactions that haven't made it into blocks yet. And then we're going to set, right? Because we don't want to just say it's equal to these self.transactions, because then when we set it to the empty list, then this gets wiped away too. So we're going to make a copy of it and then turn it into a block. And then sign it. And then return it. And so then we'll have it here in self.block. Or then we'll have it here in this block. And so this is like, and this is, so we're going to want to call handle block on it and actually save it to our own blockchain and update our own UTXO set, because we're not going to be sending a message like, you know, everyone else is going to update, so we need to stay synchronized. And then so next we need to say, we need to go and ping our peers. So we need to do basically like this ping peers. We need to do this here. And so for this, this will be like, let's be a little more formal about that. So for, that doesn't exist yet, but we'll add it. Okay, so we're going to use our old send address function, but it's going to, previously we've had a hard-coded address in send message. So if we go down to send message, oh, maybe I did add an address. So yeah, I guess I was smart about that. It already does have an address, so this works. And so yeah, we don't have to change send message. It takes an address, a command, block, and remember we already have this block command. I already updated that there, so that's good. And it sends the block, but now we just need self.peer addresses, right? These are the list of our peers, and that's where we're going to use these things finally. We're going to go in unpack that list, right? So the way we did it up here was like this, peer host name. So let's just copy that and go to the bank constructor and basically stick that in to the bank. So let me just check my work here, make sure that's right. So one little, and so instead of just getting this host name, right? Instead of just grabbing these node 0, node 1, we're going to want to also stick in a port number, because these are going to be actual IP addresses, right? The first one is the host name. Like that's usually an IP address, but within Docker we can just address the nodes by their names, which is really convenient. And then so let's put a port number in there too. And so for our code, well, do we already have port? Yeah, so we already have port. It's 902, so that's wrong. We want 10,000. So every one of these runs locally on port 10,000, right? So that's going to be our port number. And so I think these are going to need to be changed a little bit, but that's okay. So localhost port 10,000. Where are we now? We need. So here we are, peer host names. So they're not going to be peer host names anymore. They're going to be peer addresses, right? The first thing is like, so we could probably change this variable a little better. They're actually host names, and kind of make that a little better. So yeah, so peer host names equals host name and port. So they're full like IP addresses, like IP port addresses, and so yeah, we'll be able to iterate over those, and we'll be able to iterate over those here and actually pass them in, because it's a tuple. It's host name and port, and pass them directly into send message, right? And so send message uses, connects to an IP address, and so that's what will be going in there. So that all works pretty well. Okay, so now we need to go down into our main function and update this. So some of this stuff is gone, right? Bank.issue is now gone, so we're going to have to update that. And so let's do that. So that's all gone. So let's just be say like we're going to address the global bank, remember, which is, and we're going to update it. I'm not always sure when you need the global keyword, but we're just going to use it here. So bank is set as a global keyword, but as none, so it doesn't blow up when we're just using it when we're not running the server. And so let's grab bank ID, and so bank ID is here, and let's grab it from the environment and change it to an int, and let's just make sure we have OS imported. We do not, so we need to import that. And so grab bank ID, and so we're trying to instantiate a bank and do an airdrop here. And so this is another one of our janky methods in the that identities class. So we have this like bank private key. We can look up bank private keys based on their ID in like a silly deterministic way, but you can look into that if you want to see how it works. But it's just a way to get given an ID, get a consistent private key that we can kind of pretend is real. And so then we do, we also need that airdrop transaction. So this silly thing. And so we're going to do the airdrop here. And then we're going to call schedule.nextBlock. right? So we're going to start the timer of submitting blocks, right? So we're gonna when we serve, we're going to be serving multiple within Docker in a like together. It's like a constellation of these banks, right? And so it's a network, and so we're going to have a few of them, and so they're each going to start this block submission kind of timer. And so when this executes, there will be one, since we did an airdrop, there will be one block in our blockchain. So the bank with ID 1 will get like this will trigger a timer that will submit a block from their mempool, and then once that happens, then it'll be the bank with the ID 2's turn, and we'll do the same thing we're doing with the ping pong server, where we kind of go around the circle and have everybody submit their subjective view of the world as a block. And so at this point, I think we can go and I'm just going to go copy the logger from a different. Well, let's just do it here. So this code for logger, I'm just going to copy that because we're in Docker. Remember, in Docker the print statements don't show up. So so we're going to create this logger, and then within. Sorry if I'm going too fast some of the time. I just move fast. And so here, when we get a message, we're going to want to say like. Right, we're going to let's just log what message we received. And so at this point, I think we can actually run our Docker system here, and I'm sure I have a bug or two in here. So let's just look at the Docker file. So we're gonna want my BlockCoin.py instead of the default BlockCoin. So you're gonna want to edit that. But then other than that, I think we're ready to actually run Docker Compose. So if we go to the base directory, we want, because we're in the base here, and we're gonna be exercising this Docker Compose and this Docker file. So I don't know, let's just YOLO Docker Compose up, and then -- build will just make sure to rebuild every time. And so I'm sure there's going to be some problems here, and I'm sure I'm going to have to do some on-the-fly debugging, which is always so stressful. But let's see if it works. And so here you go. It's like spinning up a server here. It's installing the requirements.txt from scratch. It's doing all this wonderful stuff. Copying over all the files. Now it's going to run the server. And now for our moment of truth. Okay, so look, so we have to update our doc opt. So So I think we need to actually change. Sorry. So if you look up here, these will change to. I'm just executing a command in Vim that will change the name of the file. So I didn't know that so you have to actually specify what the name of your file is, I guess. So let's try that again, because you see we were getting these usage errors like, hey, you didn't call me by my name. Oh, no, that was not the error. It was this. This says server. We needed to just be serve, right? I kind of alternated back and forth. So that's the actual error. So yeah, so see, we changed it and it didn't go. So that's the error. Oh, and we didn't implement our turn, right? So our turn. Right, so this is where it is in schedule next block. If it's our turn, we're going to submit a block. And so our turn's pretty simple. Let's just go to the top of the definition where the properties are. And it's just if our ID is equal to this next ID, that's going to be what it's our turn. You know, that next ID just, you know, it goes from 0, 1, 2, 0, 1, 2, 0, 1, 2, right? And so we're just checking whether our ID is equal to that, and that's how we know if it's our turn. Just like a simple little helper. And we don't have the threading module. So import that. Okay, so there's one last thing we need to do to get this sucker working. Let's, instead of localhost, we need 0.0.0.0. I'm not exactly sure how to explain that. It's just like a sort of a more permissive port that will allow the process to be visible from the outside world within the Docker container. And so, or will allow the Docker containers to communicate to themselves, rather. And so now if we run it, so you'll see them attached, and then we got to wait 5 seconds for a block to come in, so it's looking good so far. And so there we go. See that? So, right, node 0 and node 2 got blocks, right? Command block, and here's the actual payload as a block, right? Because that's what node 1 starts, because that's the length of the blockchain at the beginning of time. Then it increments to node 2. Node 2 does block propagation, sends blocks to node 0 and node 1. They update their blockchains. And now we're back to node 0 because we're modular arithmetic. We go up to 2, and then once it hits 3, that just goes to 0. And then so here, node 0 sends blocks to node 1 and node 2. So now we basically have a trusted central this is like basically EOS, right? Like you have an n number of trusted validators who alternate submitting blocks. Next, we need to figure out how to talk to this from the outside world so that we can do this. Right? We don't have a way to talk. Like, if we try to do this now, right? It just doesn't work because I don't know what's going on there. That's odd. But yeah, so we're going to need to do a little more work to get that working. So lastly, we need to figure out how to connect to our little universe of Docker containers from the outside. And so in order to do that, we just need to make a couple small tweaks. I just did a little debugging and figured out how to get it working. And so first we need to change this in the handle method of our TCP handler. Let's change the amount of bytes we receive every time to 5,000. Now that we're sending, when we send a real transaction, apparently sometimes it can get above 1,000 bytes. This is a hack. In the future we'll update our protocol in order to accept arbitrary length messages. Like, you don't want this as a hard-coded variable. This is really hacky. But for our first version, it's fine. And then secondly, go to the utils.py folder. Here we're having an import from mybankcoin. That was fine for the first half of the video, but now that's no longer working because if you look at the Docker file, it only copies over certain files, and my banknet coin is not one of them. So we're going to need to change this to my BlockCoin. Okay, so we had one last bug that's preventing this from working. So if you look at this line in make block, I had a typo. This should be self.mempool. So sorry about that if you spotted that previously and had to sit and wait all this time. But so self.mempool will actually update the thing we need and clear out the mempool. Self.txns doesn't exist, right? Because this is the bank, not the block. So it's just confusing those two. So if we hop back over and run docker build, we should be able to open our terminal on the other side. Python myblockcoin.py tx Alice Bob. Alice will send Bob 10 coins, and her transaction is accepted. And if you see there, she still has 500,000 because her transaction hasn't been validated yet. It hasn't. So there, finally, it was node 0's turn. Node 0 put in its block, and her balance updated. And also, if you saw there, so in our finished BlockCoin.py file, we also have this utility where we can say which node we want to get the info from. So that's what we're usually getting it from, node 0. But we can also do node 1 and node 2. And you know, reassuringly, they all give us the same amount. And then for Bob, hopefully he has 10 more than he started with, and that's the case. So now we have, you know, this thing is actually working. And to see how that happened, you'll see that we have this option in the block, or excuse me, the doc-opt configuration --node, and we say that it's one of the options here for each one of those. And then so if we look towards the end of our file here, or excuse me, --node. So we grab that from args every time we're going to send a message. So for example, down here we grab it. This is in TX, the important one. Or we were using balance in the example, so let's use that. So here we grab that string, which node it is, and we have this external address function just above, which will take, you know, like let's say if the string is node 1, it'll just grab the number off the end of the string, turn that into an int, add the default port 10,000 plus the number, so that'll be 10,001, 10,002, or 10,000, and then it'll say localhost and that port as the pair of the address to connect to. So that's how we can connect to, and you'll see down here when we call balance, it actually uses this address, which was created using this external address function. So we're actually talking to these separate peers now. So, you know, that about wraps it up. That's everything. It's a ton of, I mean, the reason why this video took a while for me to make is that it's a lot of complicated ideas all at the same time, and they all have to work together. But if you look, we have this, you know, our blockchain, you know, 3 separate, we have a network. We actually have a network, a digital money implementation that is it's a network running on your computer and on multiple nodes. You could run these all over the world if you wanted to, and it's not really secure. There's probably holes and bugs and everything, but you get the general idea. We're getting close to Bitcoin, right? And so if you look in this code, like what's the worst part? I mean, it's this schedule next blocks crap. It's like all of a sudden our programming model is really disrupted, and we have this like threading thing that, you know, goes off into its own threaded universe and waits for, you know, schedules some function a couple seconds into the future. Like, it's really kind of weird, and like it'll be really easy for these different nodes to get out of sync or something. Like, it's just a weird setup, and it's still kind of like an oligopoly, right? You have these nodes that are basically political identities that get, you know, who knows how they get there, how you get to be one of these nodes. Like in EOS, it's really like EOS is a similar thing to this. Like, you know, it's a really political process. So we want to avoid that if at all costs, right? We want a truly decentralized, independent, anarchic, uncontrollable money, because that's what will win in the free market, right? Something that's not controllable. And so this is what we really want to get rid of. And what we're going to do is proof of work mining, just like in Bitcoin. You know, transactions can hit the mempool and never be confirmed if the banks just have some sort of like a blacklist against transactions. And, you know, doing that might maximize their profits, right? Because these are political entities that have that you know, might be able to be pressured to engage in certain kinds of behavior like this. So a better system would be to let anyone nominate blocks, right? Like mercenaries, right? And then the problem is who would assign IDs? Like we're really dependent on these bank IDs, and if people can enter and leave the network at will, that's all of a sudden a big problem. And so, yeah, that's what we need, a mechanism to nominate new blocks in a free-for-all environment. And that's proof of work. That's one of the really genius, that's one of like the 4 or 5 technologies in Bitcoin that really makes it work. It's not everything, but it's really important. And, you know, people who try to move to different systems like proof of stake or something, like it just hasn't worked. And the beauty of proof of work is that it actually works. And so that's next time. POW coin, not prisoner of work coin, proof of work coin. So that's what we're going to be doing next time. And And yeah, that's I hope you made it through the whole video. I'm sorry if anything was confusing. This is the first time we're doing it. In future classes, this will all get ironed out. And thanks to you guys for being kind of the first guinea pigs to help me teach this material for the first time. So take it easy. Post your questions on the Slack group, or if you watch this on YouTube later, send me a message on Twitter or something. Maybe Justin Moon, that's me. Thanks a lot. Bye.